Okay, unfortunately my video cut off again, and I was right in the middle of explaining these differences. Again, last section we had one of these, one of these, one of those over and over again. So you have a series of picking, I need one of these items, I need one of those, I need one of these. That's the easiest kind there is. You just multiply all the numbers together. Like 1 of 5 pastas at Olive Garden, 1 of 6 sauces, and 1 of 7 toppings. 5 times 6 times 7. In this next section, we have two similar ones called permutations and combinations. Permutation order matters, combination it doesn't. Permutation, another way of thinking about it is, are the objects treated differently, like a president and a vice president, versus are they treated the same, like you're just a committee member or you're just an officer? And if you want to choose 2 out of 9 people to do these tasks, you would write 9 permutation 2 or 9 combination 2. You always put the bigger number first. And then the two formulas are, they both have the bigger number factorial in the top, and then they both have 9 minus 2 factorial in the bottom, but combinations have the extra 2 factorial in the bottom. And you can calculate these the same way we're doing the last couple of problems, but there's even shortcuts to these. 9 permutation 2, you start at 9 and decrease by 1 until you have 2 numbers. Or 13 permutation 4, you start at 13, you decrease by 1 until you have 4 numbers. So I would stop at 10. That's the easiest way to calculate these without having to do a lot of hand calculations. So if you have 9 combination 2, the difference is you start off the same as a permutation and do 9 times 8. Stop after 2 numbers, but then you also divide by 2 factorial. So this answer would be 72, where this would be 72 divided by 2. Or you could say 2 goes into 8 4 times. 9 times 4 is 36. If you get a combination like 13 combination 4, first you do it like a permutation, and you do 13 times 12 times 11 times 10, stop after 4 numbers, and then 4, 3, 2, and 1. So I won't calculate these because they're not the problem we're doing, but that's the idea. That's the shortcut to doing permutations and combinations. Problem number 36 just gave us 9 combination 2, so that answer would be 36. And 36 is an integer, so I would put it wherever it says is an integer instead of not an integer. Here's 6 permutation 5 for number 37. So 6 permutation 5, here's how I do them. I start at 6, decrease by 1 5 times. 1, 2, 3, 4, 5. It doesn't even go all the way down to 1, even though if it did, it would be the same answer. 6, 5, 4, 3, and 2. Stop after 5 numbers. This answer is 720. Which is an integer, 720. So here they're just having you calculate these, but in a second they're going to make you figure out which one's which gets to be the hardest part. Okay, in a horse race, how many different finishes among the first 3 places are there possible if 20 horses are running? Exclude ties. So I need to choose 3 horses out of 20 for the first 3 winners. I'm choosing 3 out of 20. I'm not doing 1 of 3 and 1 of 20. I'm doing 3 out of 20. So that means it's either 20 permutation 3 or 20 combination 3. That's the first thing you want to get good at is, can you recognize when it's just 20 times 3 versus one of these two that's not 20 times 3? It's only 20 times 3 if you do 1 of 3 and 1 of 20, but we're not picking 1 of 3 horses and 1 of 20 horses. We're picking 3 out of 20 horses to finish first, second, and third. Since a horse race order matters, you'd rather be first and win more money than finish second or third. That's why it's a permutation. So on these word problems where you have to decide which one it is, then sometimes you could pick the wrong one. But now this is a permutation. I start at 20, decrease by 1 until I have 3 numbers. And if you're doing a permutation, that's all you do. If this was a combination, I would do that same thing first, and then I would divide by 3, 2, and 1. So whatever the back number is, you start there and go all the way down to 1, and then you could reduce, like 3 goes into 16, 3 goes into 18 6 times, 2 goes into 20 10. So then you could just figure that out. But we had a permutation, so we just need 20 times 19 times 18. There's 6,840 ways for that horse race to end. And it doesn't even say integer or not an integer now. They're just... These answers are always integers, so I don't even know why they were given that as an option before. How many ways can a 3-person subcommittee, so pick 3 people, out of 6? See, this is the example I mentioned. You're picking 3 out of 6, not 1 of 3 and 1 of 6. And it's just a subcommittee. It's not saying that there's a president or a vice president. That's part B. So in part A, they all have the same job, and they're treated the same. That's a combination. This is a good kind of problem where they give you a part A and a part B, and one of them order matters, one of them it doesn't. One, the objects are treated different, the other one they're treated the same. Here they're treated the same. They're just a subcommittee. Here they're treated different because we have a president, a vice president, and a secretary. But in both cases, we're choosing 3 out of 6 people. So you want to put the bigger number first, then same means it's a combination, 3. Part B is going to be 6 permutation 3. And then you start at 6, decrease by 1 till you have 3 numbers for a permutation. So the permutation answer is easier. 20 times 6 is 120. In a combination, you do that first, 6 times 4 times 3, and then divide by 3, 2, 1. And 3 times 2 is 6, so I've got 5 times 4 left. That answer is 20. So the part A answer is 20, and the part B answer is 120. An electronics store receives a shipment of 40 graphing calculators. 8 of them are defective. 4 of the calculators are selected to be sent to a local high school. How many selections can be made? And then how many will contain no defectives? Okay, so we're going to just take how many ways can you choose. We're choosing 4 of the calculators. 4 of the calculators are selected. It's just that some of them work and some of them don't, but there's 40 total calculators, and you need to choose 4 of them. So part A is just how many total ways can you do that? So I've got 40, and I'm choosing 4. And then they're just going to be sent to a local high school to be used. So they'll put all 4 of them in a box and send them there. It doesn't matter which one goes in the box first. The calculators are not being treated differently. So they all have the same job. They're all going to the high school. This is where you have to decide that this is a combination because the order doesn't matter that I send them to the high school, and they're not being treated differently. So the total number of ways you could do this is 40 times 39 times 38 times 37. Stop after 4 numbers. And if this was a permutation, that's all you would do. Combination, you also divide by 4, 3, 2, and 1. And there's always an equal amount of numbers in the top and the bottom that should be lined up with each other. You should, in a combination, you should never have 4 numbers in the top and 3 or 5 numbers in the bottom. 4 can go into 40 10 times. 3 goes into 39 13 times. 2 can go into either 38 or 10, your choice. They're both even numbers. I like 10s in multiplication, so I'm going to leave that one alone and go into 38 19 times. Or you could do all the top and all the bottom and divide them if you want, but it's easier this way. 10 times 13 times 19 times 37. The entire bottom canceled out. The top was 10 times 13 times 19 times 37. So there's 91,390 ways to send these 4 calculators off. Now, some of them may work and some of them may be defective. That's a separate issue here, which I think part A is getting into. How many selections can be made 91,390. How many of these selections will contain no defective calculators? So if we knew which ones worked and which ones were defective, 8 of them are defective. If we knew which 8 they were, we could take them away. Take the 8 away from the 40. There's 32 calculators that work and 8 that are defective. So then how many ways would you have no defectives in your calculation? You would just use 32 instead of 40. You're still going to choose 4 of them and send them to the high school. But it's 32 combination 44, 32 combination 4 if you take the 8 defective ones away. So that would be 32, 31, 30, 29 over 4, 3, 2, 1. And 4 goes into 32 8 times. 3 goes into 30 10 times. 31 and 29 are prime, so they're not going to reduce even the 2, but the 2 could cancel the 8 down to 4. You can do the same number twice. So almost every time you can get rid of the entire denominator because ones don't matter. So I'm left with 4 times 31 times, that one was 10, this one was there previously, times 10 times 29. 4 times 31 times 10 times 29. And I could have divided the 2 into the 10 too and left the 8 alone. So then there's 35,960 ways to do that, which is less than half of the ways without worrying about the defective ones, 960. Okay, so that's question 40. That's the end of section 7.4. So we've done everything in chapter 7 you need to know for this week, 7.1 through 7.4. We're now in 8.1. So questions 41 through 50 are going to be section 8.1. 8.1 is about probability. So probability is sort of what we were just doing here. This stuff is not probability, but you could use this for probability. Probability is when you do how many good cases are there over a total. I like to say good over total. Each one of these counting techniques could be a good or could be a total. In fact, that's what we could do on this last part B, this number 40, I mean, the 35,000 number, that could be how many cases have good calculators, and then the 91,000 could be the total. So that's what you do in probabilities. You try to count how many good things are there, and then you put it over how many total there are. A spinner is divided into 10 sectors of equal area. There's your total. The total's 10. That's going in the bottom. There's 2 reds, 5 blues, 2 yellows, and 1 green. That adds up to 10. We want the probability that you get a red or a yellow. There's 2 reds. There's 2 yellows. So there's 4 good things that can happen to me out of 10 total. Type an integer or a simplified fraction. This is a fraction, but it's not simplified. Divide 4 by 2 and 10 by 2. So that's what's different now, is that we're not going to get integers. Now we're going to get decimals and fractions. But you always want to be thinking good over total for probability. And I usually do the total first. So if there's 100 cans of soda in an ice chest, then you got 100 for your total no matter what. I always get the total out of the way. And now I start going back and looking for what's good for me. Good things for me are orange soda, colas, or root beers. We just count all those up. There's 21 colas. There's 12 of the orange soda. That's 33. And root beer is 22. 33 plus 22 is 55. But both of these divide by 5. 55 divided by 5 is 11. 100 divided by 5 is 20. Good over total is all you're really looking for here. There's a family with 6 children. What is the probability of having 4 boys and 2 girls? Okay, this is a little different. See if there's an easier way. I'm not sure if we're up to what I think we're up to. Let me check here. Relative frequency. because there's a way to do 43 that's different. I don't know if they're teaching that yet is the problem. I think that's later in chapter 8. Family of 6. This is actually kind of hard to do without that extra knowledge. 4 boys, 2 girls. Okay. There's 2 ways to do this, but I'm pretty sure they're not doing the easier way yet is the only issue I'm getting to. So the one way you can do it is you have boys and girls. Each time a child is born, it's either a boy or a girl. And you branch it. This is called a tree diagram. Boy, girl, boy, girl. That's just for a family of 2 kids so far. When I go to a 3rd kid, it doubles again. So there are, in a family of 1, there's 2 possibilities. In a family of 2, there's 4. It keeps doubling. 2, 4, 8, 16, 32, 64. A family of 6, there's 64 different ways that children can be born. This is the total. And when a tree diagram gets that long and that many branches, it's not actually practical to use that. So that's why I was doubting if this is how they're doing this problem. But I know the other way is taught later in this chapter, so I don't think they're teaching that yet. So maybe if we get this one wrong, maybe they would give me a smaller, it would help if this was smaller than 6 when they're teaching you this early on. But this is 64. And then we'd have to follow all those 64 paths. See how many of them have 4 boys and 2 girls in them, which is not easy to tell. Let me see what they're doing here. See, that's what I did. 2 to the 6th power is 64. They only had a family of 4. That made it easier. So then there's only 16. Okay, combination. Okay, so 4 combination 2. There's a family of 4 and they wanted 2 boys. Okay, see, that's what we did last section. So then I can do a combination to figure out if I have a family of 6, we're interested in 4 boys or 2 girls. I guess you could do either one. So if we do 4 boys out of 6 children, I need to choose 4 out of the 6 children to be boys. So 6 combination 4 would be 6, 5, 4, 3. Stop after 4 numbers. And then also divide by 4, 3, 2, and 1. 4s and 3s cancel out. 2 can go into 6 3 times. There's 15 ways to do this. This is the good cases. 15 ways to have 4 boys in a family and 2 girls. And then the total is 2 to the power of however many kids there are. I thought there was another way to do that at this point. There's a different way to do that kind of problem that they're going to teach you later in this chapter, but I knew that we weren't up to that yet, so I didn't want to explain it when we're going to be doing that later anyway. Okay, so this problem, I think the only difference here is instead of telling me the number of each of these categories, like the number of colas, usually they do it like 42 and they say there's 21 colas and 12 orange and 45 ginger ale. What they've done here is if there's decimals, they've already divided them by the total. So, and they didn't even tell me what the total here is. So we want the probability that somebody will choose J or P, and J is 0.29, P is 0.26. They've already been divided by the total. So if they're decimals, you can just add those decimals together, and then you got a 0.55 probability of getting one of those two. So this one's a little easier because they've already taken the time to divide by the total. Normally what you would do is you'd say how many J's are there, how many P's are there, add that together like the cola and the orange soda, and that would be your good cases, and then you would divide by the total. But we could have also done number 42 this way. In number 42, if I would have done 21 divided by 100, 0.21, and then 12 divided by 100 is 0.12, and then 22 divided by 100 is 0.22, that's what nice thing about 100. If I would have done 0.21 plus 0.12 plus 0.22, that would have been 0.55, and that's what 11 divided by 20 is. So that's this problem. 44 is just like 42, except they've already divided by the total for you. Once you see decimals, then that's what's happened. Okay, small combination lock has 5 wheels. Remember this? We had one of these already. Each labeled with 10 digits. Okay. If an opening combination is a particular sequence of 5 digits with no repeats. See, when we had this problem before, it was how many ways can you do it? Now, what's the probability of somebody guessing the right combination? So that's why the previous chapter was how many ways can you do it? So you could possibly figure out the good or the total in a probability. In fact, the one about the family we just did one where we used a combination to figure out how many good cases there were. It's more common actually to use that to see how many total cases there are, or one of these other counting techniques. So I have 5-digit slot to fill in. Each one gets a 0 through 9. And then does it say repeats or not? No repeats. So then you just go 10, 9, 8, 7, 6. This is your total number of ways to set a combination on this suitcase. 10, 9, 8, 7, 6. There's 30,240 ways to do that. That's what we did last chapter. Here we have one extra step. Probability, what's the probability somebody guesses your combination and can open your suitcase up? Well, there's only one combination that you can set at a time on your lock. So they have a 1 out of 30,000 chance of guessing your combination, which is pretty low. 1 divided by 30,240 is it's scientific notation. It's so small. So it's actually 000033 and so on. It would have 4 zeros before you got to the 33 part. This is tens, hundreds, thousands, 10,000. There's a 3 in 100,000 chance they would guess it. Type of fraction. Okay, they don't want a decimal because it's messy. 1 over 30,240. So that's exactly the point of why they brought this problem up again, is we did this problem earlier today with how many ways can you do it. We were actually figuring out the total number of ways. And then just like your chances of winning the lottery, you could figure out how many ways are there to win the lottery, and you buy one ticket, your probability of winning is 1 over that big total number. An experiment consists of rolling 2 fair dice and adding the dots together. Okay, find the probability that the sum of the dots is a 9. Okay, there's an easy way to do. I call this the sum of 2 dice. Sum of 2 dice. You can also do 1 die, but sum of 2 dice. Once you get a problem about sum of 2 dice, I make on my scratch paper, if I was taking the test, I would make a little chart on my scratch paper and list all the numbers between 2 and 12. Because that's all that can happen. If you roll a 1 and a 1, that's the lowest you can roll on both dice. 1 plus 1 is 2. If you roll a 6 and a 6, that's 12. The sum of 2 dice is always between 2 and 12. And this chart is very helpful for finding these probabilities. If you just make this, probably on a test there's going to be like a part A, a part B, a part C, where you're going to have to do this multiple times. So if you make the chart one time, then you have it for any possible question they could ask you. It turns out that the chart's symmetrical from the outside in, which helps to fill it in. And the first case is 1 out of 36. It turns out 6 times 6, 36 different ways to roll 2 dice. And there's only one way to get a 2. There's only one way to get a 12. And then they just repeat on the outside. Then you move your way into 3 and 11, and you add 1. So both 3 and 11 happen 2 out of 36 times. 4 and 10 happen 3 out of 36. It's as easy as counting 1, 2, 3, literally. And keep moving in. 9 and 5 are 4 out of 36. 8 and 6 happen 5 out of 36 times. The most likely thing with 2 dice is 7. That happens 6 out of 36 times. And there's various questions they can ask. This is a real basic one. They just wanted, the sum is a 9. Literally a 9. It's right here in the chart. The answer is right there, 4 out of 36. And I don't reduce here because you might do more with this stuff. But after you get that answer, then reduce it. In the final step, reduce it. So 1 out of 9 is the answer. But they could also ask, that was the probability of a 9. We could do probability of a 9 or a 12. Then don't reduce yet, but you write 4 out of 36 for 9 plus 1 out of 36 for 12. That would be 5 out of 36. And this is why you don't want to reduce first, because if you made this 1/9, then it's hard to add 1/9 plus 1/36. So that's what you could do. Or you could say, what's a chance you roll an odd number? What's a chance you get a 3, a 5, a 7, a 9, or an 11? That's an odd. The probability of getting a sum that's an odd number, it's going to be over 36, and you just add the tops. 2 plus 4 is 6, plus 6 is 12, plus 4 is 16, plus 2 is 18. There's a 1/2 chance of an odd, and that should make sense because evens and odds. There's a lot of gambling games that do that, and if one of them was more than 50%, people would pick that one. So this one only asked for 9, but maybe we'll see another problem where it's sum of 2 dice. Now, this is not 1 out of 9 because this was a 9. Don't be fooled by that. Yep, see, here's another one about 2 dice. So now we want less than 6. So you can either click this, and the problem with, see, this is the real chart. There's 36 things here. But the problem with this one is, I don't like this, I don't use this chart because each one you have to add yourself. You have to go to one and say, okay, 5 and 4, that's a 9, and I'm trying to get, what was it, less than 6. Now that one's not less than 6, okay. 4 and 1, that one's less than 6, but 6, it's just harder to work with this chart. But there are 36 things here. This is the only one that adds up to 2. This is the only one that adds up to 12. These two add up to 3, and these two add up to 11. That's why they're 2 out of 36s. So if you want the probability that the sum is less than 6, I would go to my chart instead of their chart. Which of the numbers between 2 and 12 are less than 6? 2, 3, 4, and 5 are. So all you have to do is add those together. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. There's a 10 out of 36 chance you're going to get less than a 6 with 2 dice. And that reduces to 5/18 if you divide both by 2. So notice I'm on my second consecutive problem about 2 dice, and I had my chart already ready on the scratch paper. So then I didn't have to start all over again and start recalculating from the start. Here's another 2 dice problem. Now we want a sum that's greater than 11. This is an easy one. Greater than 11. The only number here that's greater than 11 is 12. So it has a 1 out of 36 chance. I just have to look it up. That's why I like that chart where you can just look up answers part after part after part. Question after question after question. That's all about 2 dice. Okay, probability you get a sum that's equal to 1. Now that's an issue. There is no 1 in this chart. You literally cannot get a 1 if you roll 2 dice. If you roll 1 dice, you can, but not 2 dice. So the probability of a 1 when you roll 2 dice and add them together, this is a concept. There's 2 of these. Sometimes an event you're trying to do in probability is completely impossible to happen. I cannot roll a 1 with 2 dice. If an event is impossible, it has a 0 probability. That's the lowest it can ever go. And let's say I take out a coin. Heads, I win. Tails, you lose. That little famous joke, heads, I win. Tails, you lose. So if heads or tails comes up, I win. That's 100% of the time. That has a probability of 1. If it's certain to happen, it has a probability of 1. Most probabilities between 0 and 1, but it can be exactly 0 or exactly 1 if what you're trying to do is impossible or guaranteed to happen. This is impossible, so it just automatically has a 0 probability. If I said try to roll less than a 13, all of the numbers are less than 13. So then the answer would be 1 if that were to happen. Okay, so... Okay, we're more than 2/3 of the way done, and there is one last question here in section 8.1, but I know we're well over an hour already in this video, and there's only 21 questions left, and it's going to take me a while to read all this and see what they even want here. So this is a good stopping point, and this is the end of the Tuesday, July 26th video, although I had to do it in 2 different videos because my camera ran out of space on the first one somehow. So I'm signing off for today, and tomorrow we'll do 50 through 70. There's 21 problems to go.